All right, to start with, we need to define the loss function. The most commonly used loss function is called the likelihood function. What is the likelihood function? If you go to Wikipedia page, a likelihood function measures how well a statistical model explains observed data by calculating the probability of seeing that data under different parameter values of the model. What does it mean? In our case, the likelihood is simply the product of the probability for all the possible character pairs in our data sets. In practice, it's usually very hard to maximize the product. So we take the log of the product to turn it into a sum. And since the log function is monotonically increasing, maximizing the product is equivalent to maximizing the sum. Our final loss function will be the negative of the log, which is the negative log likelihood function. And our final goal will become minimize this. Let's take an example. So we iterate through all the possible words in the entire data sets, and for each word, we get all possible character pairs and retrieve the probability for that pair. Remember, we have built a bigram that logs the counts of all possible pairs in the entire data sets. And from that counts, we can calculate the probability. We take the log of the probability and sum them all up to get the likelihood for the entire data sets. Here we have printed out all the possible pairs for the first word in the data sets. And there are in total 228,000 of pairs in the entire data sets. The negative log likelihood is a very big number. So usually we use the average negative log likelihood by dividing the number. So we get 2.4543 as the negative log likelihood. Now we have defined our loss function. Let's create the training sets. Since we're simply using one character to predict the next character, the training sets are quite straightforward. Input will be a sequence of characters, and the output will be the sequence of the next character in the input. In this case, if we look at the first word, after we turn the character into indexes, the X will be the index of each character in that word, and Y will be the index of each following character in that word. We simply take the probability in the data, take the log and divide it by the number of samples. Here we get 2.151. All right, let's get to the optimization step. First of all, we initialize a parameter matrix of shape 27 by 27. It's sampled from the normal distribution. As you can see, there are negative numbers, so it's nowhere near the probability that we want to get. A standard way to turn this matrix into a probability matrix is to, first of all, put each element to an exponential, so we can get rid of the negative sign, and normalize each row, so each row sums up to 1. We can further demonstrate that the probability that we got all sums to 1. Now this method is essentially a softmax method. We will see a lot of softmaxes in the neural networks. Right now we have the probability matrix. Loss function is simply retrieving the observed probabilities from our data sets. Take the log and take the average. If we run this cell, we can see it's 4.46. Remember, in the bigram, we calculated the negative log likelihood as 2.45. So 4.46 to 2.45. There is still a lot of room to improve. How do we improve? We use gradient descent. So gradient descent it's simply calculating the gradient of the derivative of the loss function with respect to a W matrix, and update to get the gradient of W and update the W by decreasing a certain amount of gradient. We can run this and then calculate the loss function again with the updated W. All right, so 4.24 is smaller than 4.46. Let's run again. Let's calculate, update again. As you can see, the loss function is decreasing, which means this gradient descent is working. In production, you never want to manually run this backward process again and again. The way is to set up a optimization loop to run it automatically. So let's get right onto the optimization loop using a full data sets. Now we have, if we use the full data sets, we have 228,000 of the data points. And like we did before, we put this backward process and up gradient descent into a loop. We let it run it again and again. Originally, notice that we introduced a new variable. Here, it's called the learning rate. It basically controls how fast you want to update the data. This is the hyperparameter you need to turn. You need to adjust for the model to achieve its optimized performance. Now, it seems like our learning rate equals 50 is the good one. Let's run this. As you can see, the loss function keep decreasing, which means this optimization works, and it will keep optimizing the W until it reaches the optimized point. After 500 iterations, let's sample from the model. Previously, the P is sampled from Bigram. If we sample 10 words, that's what we get. And now we replace this P matrix with a P net. P net is calculated with the updated W matrix. And then we sample it again. The words are the same, or nearly the same. The first two words are the same. The third word, it starts to, slightly different. Previously, it predicts the end of the word. Now it predicts another character. However, the rest of the word are also the same. So the network is working. It's starting to mimic the Bigram that we have built. If we look at the sample of the results, they start to look like the name, but they are still quite ugly. That's because we are only using one character to predict the next one. So in the next series, in the following videos, we will increase in the context to predict the character. Instead of using one character to predict one character, we are using 2 characters or 3 characters and even more characters to predict the next character. And in that case, Bigram is not possible to achieve. We will use gradient descent and use a more complicated network structure for that work.